So we thought we'd present a unified sort of example in line with DSA, our end-to-end type of methodology of how you can think of a project like this project of characterizing images or numbers in this case, and where are the numbers? Yeah, so numbers taken from the internet or written on paper, and you can sort of use some pre-processing, some computer vision, some image processing mainly to sort of threshold and make them clearer so that your data set is more usable. Right, so this was the goal. And you know, we also looked at several other images that you can sort of do this with, or other techniques of image processing. And so the idea, so do you have this, do you have a setup of TensorFlow running? Do you have a notebook running? Okay. Do you have TensorFlow? If you import TensorFlow, does it come? Yes. Okay, then we can sort of do some of these experiments. So my goal was really to take it from here and try and introduce some deep learning methods, or continue from where Ben stopped. How can we better this process by using deep learning? And that's where I start from. So before we get to convolutions, I had a small, yeah. So I had an example here. So what is deep learning? So yeah, what is deep learning? What's this whole deep learning thing? I'm sure we've all sort of run some notebooks on this and this kind of thing. You know, what is it? Why is it good anyway? Deep learning. Yes, sir.
That is a sign of machine learning. Most of the time, when we have a complex data, next to neural network, deep learning is recommended.
When we have a complex network. Did you say when we have a complex
network? Complex data.
Complex data.
Yeah.
So when we have complex data, maybe it's good to try a deep learning sort of model. All right, so yeah, maybe. So, I mean, deep learning is part of machine learning, and the whole point of machine learning is to take some sort of data set and infer some sort of underlying, you know, model, right? So we assume, you know, data, whichever data is seen, you know, there's probably some sort of underlying model that creates that data, right? So if you take an example of what's a good example? So let's take DSA, all right? So maybe attendance, right? So maybe we want to predict attendance in DSA, right? And maybe we have on this x-axis maybe funding. So the idea of so this is fairly complex. I mean, you know, it's very hard to predict the attendance of DSA generally, right? Because, you know, there is no real function that sort of does this. But we can assume there's a function behind why people come. Maybe it's funding, maybe you're near here, maybe you're interested in this thing, maybe it's the instructors. You know, we can assume there's some sort of motivation which we can't immediately observe why you come, right? So let's say attendance is based on funding. Let's build a simple model. So if we So machine learning requires us to collect some data. So we'll collect some data, maybe from the previous data science Africas. We sort of look at the attendance and how much funding we had for DSA, right? And maybe if we get the data, we start plotting some sort of, you know, maybe this is the data for the last couple of years, right? So what does this trend show, basically? What does this graph show? Yeah? Attendance increase with funding, or funding increase with attendance. All right? The what? Nothing increase with funding. Funding. Right, so maybe attendance, you know, maybe there is some sort of correlation between attendance and funding, right? So when we have more funding, you know, maybe we can pay for more people and more people can come. So attendance tends to increase, you know. Maybe this is one hypothesis. And so from Neil's talk yesterday, we had a curve like this for, I don't know what it was. Was it the runners? No, the runners were something else. Anyway, but we had this sort of thing. So you can think, what sort of model can I build to, if I wanted to predict how many people will come next time and I have an idea of funding, what sort of model can I build here to give me this sort of prediction? What? A new? Linear regression. So we could do maybe linear regression, right? Get a linear regression line somewhere here that sort of describes the data, and we can sort of use that to predict maybe the number of people who will attend next time, right? And so this is you know, taking a model, a machine learning model, or taking some data and building a simple model from this data, right? But we can also assume, so this model can be anything, and this is sort of the idea of deep learning, that you can also have this as some sort of neural network. Like this could be a simple model. We could describe it as a simple model where you have one neuron that takes in some sort of funding and outputs attendance. So this could be the idea, right? That, you know, you have some, and then your neuron is sort of the magic that's sort of doing this line. And maybe, you know, our model actually doesn't, you know, go below 0 because, you know, that does not mean much, right? So you have maybe a neuron, could be one neuron that does this, right? So this would be a neural network, right? And we could even program this thing here and build a model that does this with one neuron based on this. Very simple model, right? So I guess the idea with these deep learning models is really, they're very good function approximators. So they are sort of these generic function approximators. When you have a complex, you know, some data that, you know, you want to discover what sort of underlying function generated the data, you could use these neural networks out of the box and, you know, plug them in. And that's why they are so good, right? That's why they work quite well most of the time. So they are able to discover these functions in these deep spaces. All right, so one idea I want is for us to actually code this up and see it run. All right, so let's code this up, maybe with a simple TensorFlow network. And so you can also do it on your machines. That's why I was really keen. All right, so we want to build maybe a very simple function. All right. All right, so want to see if we can build a very simple function. A function, we could represent this by some function that takes in some input and comes out with some output, right? So let's build a very simple type of function. Some function of x that, you know. So what's a good function? What's a simple function? Something like that? Okay, so now we have a function. We've built a function, some simple function of x. So it has one input and one output. So for any value of x, we can, you know, it will give us some result, right? So we actually know the function. You can assume this is an underlying function. Our goal is to generate some data and see if we can build some sort of neural network to discover this function. That's the... All right. All right, so we could come up with some random data. etc. Right? Let's say we have very simple data like that, and we could our values y would sort of look like that. So we want to build this very simple model. So we can So I think Benjamin talked about sequential models. Is there anyone who's unfamiliar about these sequential models? So Keras basically, you know, Keras now is part of TensorFlow 2. Keras is sort of an API for building these sort of interfaces for deep learning. So you could have a sequential model. Keras sort of has these sequential or functional APIs, but a sequential model basically just means there are these layers that you can layer together, right? Just sequence of layers that you can put together. So we could build a very simple model with just one layer, right? All right. All right, so we are building this we are building exactly this thing here we saw here. Oh, that's a mistake. We are building this thing here we saw. So we are saying we want to build one neuron, so one unit, which is this neuron. We have our function. We have some data that we want to put in. It's sort of just one dimension data. And want to build this model, want to build this sort of model and see if we can predict the function that's producing this data. All right, so the this thing has a good, you can also see roughly what we're doing here. So what we are going to try and build here with this model is essentially so we're going to assume some sort of linear model, for example, hopefully. That is some function of x plus, you know, some bias, right? So we're going to assume we have, and that's why there are sort of two parameters. So you have one parameter, which is sort of this w here, and this bias term, which is the second parameter. So we're going to try and predict or get these parameters for this type of model. All right, and to do that, we need to compile it, right? So what loss do we need here? Are these losses and optimizers common? What loss would we need here? Yeah? The what? Mean squared error, right? Is there anyone lost here? Are you doing this? Are you sort of coding this up? It's just one line, two lines actually. Okay, so we want to see if, so what we are trying to do here is, so we have some data x, right? And we have some data x and we have some data y. So based on what Mike said, so we have labeled data, we have our data x, we have our output y, and want to see if we can build this model that is sort of creating this data. In this case, we already know the exact function that's creating this data, and want to see if we can recover it from a very simple neuron, a very simple neural network. So we can fit our data, we can run it for, you know, a bunch of epochs, it runs. So how do we test it? We can get a random number, maybe 45. Oh. Okay, if we get a num x, if we have an input 45 into our function, this function here, we get some number like 228. Want to see how well our model does with this same number. Okay. So we do horribly. So why do we do horribly? Shouldn't it work? Try what? Small iterations? What do you mean? There? The loss is too large. Right. So what should we do? Train more? All right. So the loss has reduced. Try it again and see. So it has sort of improved a bit, right? Can we improve it more? Can we train it more? So this is so easy to train because it's such a small thing. Is it done? Yeah. All right, now we are overboard. Right, so we can sort of keep trying to train this thing. Man, it worked when I was doing it in. It always works offline, huh? It doesn't work online. Let's try another. Okay, this one, very small input, So, so basically the idea here really was that what I was trying to show here is that that these neural networks, even without knowing what the function is doing, right? We just built a very simple model. We fed it our data, and this is very little data. So one way of increasing the accuracy of the model, apart from training it more, could be to increase the amount of data we have, right? So if we increase more examples from this function, then we can probably get it more accurate even with less training. Yeah, but the idea was that we can. So the model has somehow figured out the function, right? So the model has somehow figured out what function created the data and can predict very accurately sort of the results that come from that. Any questions on that? Okay, so we have a very simple model here. Let's try and broaden this model, right? So we could have, so we assumed, attendance at DSA was sort of related to funding, but you could assume many other things, right? So, we said funding. Yeah? So funding was a big thing, but you could also think, someone called this the winter, DSA winter, right? So, because it's really cold here, apparently. So you could think maybe the weather also affects, attendance, right? Maybe these two things have some sort of effect on maybe something like location, right? Right. So funding, if you have enough funds, then maybe we could take this DSA to, I don't know, to a beach in maybe next time to some beach far away in Greece, right? DSA in Greece, Maybe funding affects location, so does the weather, right? But maybe you also have other things. Maybe number of instructors. Maybe you could also think of, the number of instructors coming. Maybe this has some effect on the attendance. Maybe it affects sort of number of talks, How many talks are given at DSA? Depends on how many instructors. Maybe you also have other things like devices. We have devices from ARM, right? Maybe this also affects attendance. When people hear, ARM is going to come and give out free sensors. Oh, mechanism design. I should have put mechanism design here. You're going to give out free dollars for mechanism design. But you can think of devices, and maybe these devices affects how practical DSA is. Yeah, so practicality. And maybe also the instructors sort of have an effect on how practical DSA is, right? And so you can think these things here could sort of have an effect on attendance, right? So originally we had a very simple model or a simple diagram with funding affecting attendance, right? But you could think that there are many other sort of things that are interconnected that could affect the attendance at DSA, right? And so this, you could think of this sort of as a network, right? And if you think of these things, these nodes as neurons, then you could think of this as a neural network, right? So you could come from our small network we had with one neuron, and you could make it deep, right? So the depth of the network could describe in more detail what things sort of affect attendance, right? And so you could have, maybe these could eventually be your hidden layers, right? And then you have your input, you have your output, and then you have some sort of hidden layers. And these layers could be several things. So location could affect visa, maybe visa, how easy it is to get visa here, which affects attendance. And so it could be really deep, right? So this is sort of an idea of, and what deep learning helps is that you give it the inputs and you give it some output, and then it sort of tries to learn the things inside here. And you can sort of break this down by describing how many units you want inside here, what the different layers should be doing. Should they be conv layers, or the dense layers, etc. So the thing we did was a dense layer. So you can think of this. So if you wanted to create a dense layer from, or a dense sort of neural network from this, then you could connect everything to everything, right? And this is what happens when we create a dense layer like this one, well, a dense model, right? So when we say we are creating some sort of dense layer, it means we are connecting everything to everything. So the beauty with neural networks is that they can sort of figure out which links are most important for predicting our attendance.
So for the philosophy of deep learning, does that mean the method or the architecture is based on a neural network? Or do we see certain other, is it predominantly derivative from neural network architecture?
Derivative from?
In terms of like the field, so this is a neural network and the interaction of the neural network.
Mm-hmm.
Do we see any other methods or architectures that would, be considered under the bracket of deep learning? Or is it specifically that?
Well, there are very many sort of types of architectures, that are optimized for different things. If you're doing sequence learning, then you have sort of a different series of architectures. But I think that the goal with the architectures is really how do you get from the input to the output. And if you have a very deep network, maybe you use ResNets that have these sort of recurring things that keep transferring the gradients down. Anything. So what I think a lot of research has been in sort of figuring out what architectures work. And I think this is still an open field. It's sort of like black magic because, it's very hard to understand what works and what doesn't work. But people have figured out that creating them deep really works. Or some networks work, some architectures work better for certain applications. So for example, for images, we're going to use convnets. So this is sort of same layers, but different types of computations happening in those layers, right? So it's so we're going to see some ways in which you can sort of run over this problem of discovering architecture. So discovering the architecture which is best for your problem is sort of a hack. So you sort of try different things. There are sort of best practices of how to do it, but generally it's not a straightforward thing. All right. So from all those things, so basically what we've said, we could have multiple, you could have multiple inputs into this this sort of network. So you could have different sort of x's. Yeah? You could have x1 representing funding, x2, blah, blah, blah. And your goal is really to figure out some sort of linear, some linear mapping between the output and the inputs, right? And this sort of tends to look something like this. So given, if you vectorize this x, and this is x, and these are the weights that represent how important each of these features is, so the weights are sort of calculated from here, how important each of these is for attendance, then you could think of your, a description of your neural network like this, right, in some way. So the idea here is, given some data, so given some data like we had x and y, right? So we had several examples of x and y. So given several examples of x and y, we could think of how do we train this network such that the predicted value is very close to the value that we're using for training our labels, right? So you could think of, if this is sort of our network, then what we want to do is calculate y hat, right? So given this example, we want to calculate y hat from this thing that gives you, and compare y hat with sort of yi, right? So y hat is our prediction given our network, and yi would sort of be the label that we're trying to predict, right? And this sort of is the training. So in the training, we're trying to get this as close as possible. Yeah? Get this value we're estimating as close as possible to the y, right? And to do that, we calculate some sort of, how do we do that? How do we do this? How do we sort of measure how close these things are to each other? Variance? Yeah, sorry? Do we have what? Weight adjustment. Yeah. Right, so we are weight adjustment, but what should motivate our weight adjustment? How should we adjust? Yeah? The squared error. Entropy loss. Yeah, the guys yeah. Next time we'll start from, here and start moving upwards. So yeah, so you calculate some sort of, loss or similarity matrix, metric, right? How close are these things together? How close are they from each other? Because you want to predict this, and this is your prediction of this, right? So you can think of some loss function, right? Someone said entropy loss, mean squared error. This is the idea of loss, and this is the loss we put here, right? If in our simple network we find the loss while we are compiling the thing, so we said, what loss do we want to consider when we are calibrating, or when we're training our network, right? So we get some sort of loss here, right? And it could be mean squared error loss, where basically we're saying what's the distance between the two, right? So the smaller this is, right? If these are very similar, then this tends towards 0, so it's small, right? And once we have the loss, then we need to change the weights. So someone talked about sort of modifying the weights. And in order to modify the weights, then we need some sort of optimizer, right? So we need some sort of algorithm or another method that takes this loss and takes the weights that we initially guessed right, and tries to adjust them such that it minimizes this loss, right? And this is the goal of the optimizer here, right? So that's what the optimizer is doing. And here it's stochastic gradient descent, right? So eventually deep learning or these sort of neural networks break down into these main sort of blocks, right? So one, given some sort of input and output, you need to define some sort of loss function, right? So the loss function relates your predicted value to your training label, right? So it could be mean squared error. When is mean squared error the right thing to use? When is it a good thing to use mean squared error loss? What kind of data do you want to be using that on? What kind of problem? A regression problem, right? So a regression problem like the one we had here where you're trying to predict number of people who will attend is sort of a good place to apply mean squared error. But you could also have someone talk to you of cross entropy. When would you apply that, for example? When would you apply sort of an entropy loss? So maybe a classification problem, right? So if our problem here was different and was classification, so maybe attendance was, you know, maybe 1 and 0. 1 that you attend, 0 that you don't attend, then maybe we need a different type of loss, right? We need a different type of loss to quantify that sort of error. So eventually, if you're building your own sort of neural network, one idea is really figuring out what sort of loss you need, right? So the loss you get sort of has a bearing on how well your model gets trained, right? So you can come up with your own loss, right? It just has to be something that can decrease as you improve performance, right? And you can train it with so many other optimizers. So in these days, all these tools, you know, TensorFlow or PyTorch or whichever have so many sort of things you have to figure out here, right? They have so many options you can apply for these optimizers and loss and metrics. And so deep learning now is sort of a lottery of figuring out these things, right? In some sense. All right. Yeah, so once you have those major things, then you can build deeper types of models. All right. I think that's sort of an intuition of why the main things you'd need to consider without going into a lot of the math. All right, so today, you know, we want to look at convolutional neural networks. So my battery is going down, but so the convolutional neural networks are sort of another type of, you know, deep neural networks that are really good for images. And why are they good? Because they have this idea of convolutions, right? And so what are convolutions? So in our previous thing, we saw a dense layer. We're applying some sort of dense layer. But you can see there are so many other layers here. And I'm sure you're sort of used to these layers or you've used them before. But why are convolutions good for images? What are convolutions? Linear functions. Right. But why are they so good for images? Or why is it so good for, you know, why are they good for images? Why are they? They call Right. So convolutions are pretty. So they're good because they allow for this translation invariance. Let me try and get those images. Right. So convolving basically means applying a small filter or some sort of filter that you move across the image in some sense. And basically it calculates the same type of convolution for each of the areas. So if you have some features that are the same in any place, then because you're using the same filter to move over the image, then you get this sort of translation invariance that you can extract the features from anywhere in the image. And so this helps with building the model, right? Because these images have unique features, right? So calculating is zero. Someone is trying to explain what these features are, but they're unique. And if you can sort of extract them from an image, which is sort of in any way, then you're likely to build a better type of model, right? And what do these, so I wanted to give a quick example before my computer shuts down. So these so the convolutions, basically, if you have an image, so an image is a bunch of intensity values. So you have several values in this. Well, this image is a bit, but if you had a small filter, yeah, you can't think of applying this filter on this image and sort of convolving it around this. So if you had values here, 3, 4, well, 32, etc. And you had, some filter, then applying this filter here extracts certain features from the image, right? So a filter like this, for example, extracts vertical lines from an image, right? So the idea is really to apply many, many filters to this image and extract many types of features from this type of image. And I can show a quick example here. So if you look at this, so I took one of the images. So you can get this convolve thing from SciPy or from anywhere, right? So I took an image, one of the images, and applied a filter to it. So I have this filter here. Where is the filter? This filter here. Where is it? Right, so I have a filter like this. So this filter looks exactly like the one I've written there. So it extracts vertical edges. So if you take this image and apply the filter to it, then if you convolve this image with this filter, then it will extract certain parts of the image that are interesting for that filter. Right? In this case, it extracts sort of vertical lines. Right? If you apply another filter, maybe a horizontal filter, you can apply, there it goes. Yeah, anyway, so what I wanted to show there was if you apply a different filter, it extracts different types of features from your image, right? And this is why convolutions are so amazing, right? They can extract multiple features from the image. So what generally happens is when you create these layers, these convolutional layers, you describe how many filters you want. And these filters are initialized, based on some best practices. And from there, you can extract multiple sort of features from your image. Right? And for example, what I showed was extracting, vertical edges, could extract horizontal edges. If the number sort of has unique features when it turns, you could extract those. If it's an image of a a cat or whatever it is, it could extract the eye, it could extract different features. And by doing this over the depth of the network, you can get a model that can accurately predict the class given an image. Right? This is why it's quite good. Oh, nice. All right. So the goal of the continuation of the lab was sort of to go through those steps. So if you have the notebook, basically is to try to run these convolutions. So one last thing in the notebook is this idea of two ideas. So one is image augmentation, right? So sometimes like in our case, the amount of images being collected were maybe 9 images from each of the digits. So these are not nearly enough to do a very interesting model, very deep learning model. You need a lot of data, train these things accurately. And so one idea really is to create more images. And sort of Ben talked about varying the images. If you got the image and sort of rotate it slightly or change the color, then you can create multiple images which look like the training data, but they are sort of modified differently. And using those images, you generate more data and you can train a better model. But someone asked about how do we get the right architecture. So architecture is very complicated to get. You can try simple architectures, or more complex architectures, and make sure you don't overfit. But one idea is to try so the notebook goes into transfer learning. So this idea of transfer learning, that people have built these networks using images from, which have been published online, for example, ImageNet or other types of image libraries, and people have built networks for these things, right? So you have very deep networks that have been built maybe over weeks, over several months, or over several GPUs, and we can take advantage of that learning, right? So instead of crafting an architecture from scratch, you can sort of take one of the architectures from an existing model, and you can train the last part of this model to suit it to your data, and using that you can sort of see accuracy gains or performance gains. And the notebook sort of shows these things, right? Oh, we're back. Yep.
Which kind of problems can use a keep level for?
Okay, hold on. It's a bit. Oh no, it's not it. Yeah, that's it. Yeah, sorry. Yeah. Mm-hmm. Which type of problems? Recommended solve deep learning. You want to answer? All right, so, okay, so maybe I'll answer those two questions. So which types of problems are good for sort of deep neural networks? I think most of the problems where you can't so deep learning, these deep learning models are really function approximators. So if you have any sort of data where you need to predict something, or you have some data where you need to relate something to a label, they're really good for this kind of thing. And they've been shown to work with, you know, images, with sequence data, language mining, audio data.
Minimize the false positive.
The what?
You mean it's minimize the false positive when you use it? False positive.
Does it minimize the false positive when used? Yeah, I mean, that's the performance. So whichever metric you're using, they tend to work better than most other methods.
Because it brings for us complex.
Mm.
Then sometimes you do something additional cost you don't need.
Yeah. So I guess this is what Neil was talking about yesterday. So it depends a lot on the type of problem you're working on, right? So some problems can be solved with very simple models, and generally that's the best thing to do. Some domains really like very explicit models that can be explained. Like in the medical domain, they use decision trees very, very much. All right? So even bring a model that's showing an accuracy greater than a decision tree, they still have to be convinced to take it, because they want to see exactly how this thing is doing, creating a decision. Other things where, you know, you're doing random prediction, well, maybe not random predictions, predicting things like which book you're going to buy next, where the network may be a bit, opaque, you can't see it, and maybe where if you buy the wrong book, the cost of buying a wrong book may not be too high, then, there's, I tend to think there's less concern, for example, about how the model can be explained. But I think it's a case-by-case basis. But I think the idea is normally try a simple model and then go to a more complex model. But even with deep neural networks, trying a simple architecture is normally the first thing to do. You try something simple and see what the accuracy is, right? Some of them can be done without, putting a huge network in the middle of your processing. So as regards transfer learning, so transfer learning, there are several ideas. So the idea of transfer learning is, let's get that network. So this is an example of a network. So a very deep network, VGG. So what people will do is, depending on how much data you have, so if you have very limited data, you'd probably keep all this thing fixed, right? So the idea with transfer learning is that you take the network architecture, but also the weights that has learned, right? So if someone trained this thing over a month, they have learned certain weights in this architecture here that you really are interested in using, right? So you take those, and then you take maybe the last bit of it, maybe the dense network, or you can even go up to the end and just change the prediction, right? Change the softmax. So if you have a VGG network, it's a big network, but at the end it has strained on ImageNet, it has some softmax here that's predicting, maybe a 1,000 class problem, right? So it's predicting, it returns a vector of 1,000 numbers. You could change this and say, okay, for my problem, here I'm doing only 9 numbers in Aramaic, right? So I could have another softmax here, take this out, put mine, that does only a 9 class type of problem, right? And then you'd freeze all this, the whole network, and retrain it with the little data we have, right? And this is what we sort of do. Train it with the little data we have and see if it can perform well. If you have relatively more data, then you can shift, you can go further into the network. So you can say, I'm going to freeze all these layers, but I'm going to unfreeze these ones and train them.
Actually, in this case, you are adopting the existing architecture.
Yeah.
So you are not transferring the knowledge from one domain to the other. And if you are using the trained way as it is to some other task, so some what is happening, or using some part of the model, you can say it as a transfer learning.
Mm-hmm.
But if we adopt the existing architecture as it is, just changing the last food connect or the prediction layer, can we say this as a transfer learning?
Yeah, it is. So what happens at these early layers? You know, maybe understanding what the layers are doing.
Minimize the dimensions.
Yeah?
To make it easy.
Minimize the dimensions.
You have to speed the process, speed up the process.
Right. So what the neural network does is that it creates representations of your input data as it goes along, right? So these images we're talking about, I mean these features we're talking about. For example, the features we're extracting here, like I showed, maybe it's just edges. Maybe you're extracting horizontal edges and vertical edges, right? So even this big network, right? At the front here, it also was doing that. So you can, I mean, horizontal edges and vertical edges are not specific to any problem or any type of image. Any image can have these types of features, right? So the idea with transfer learning is to take models where people have learned sort of similar things, right? So if you're doing images, in this case, ImageNet has a bunch of images, for example, for cats, or I don't know if they have for numbers, but you can take this idea and extract the features that are really, so this thing has been trained optimally to extract maybe weights or weights that represent horizontal lines, vertical lines, and other sort of representations along the line that are agnostic to the type of problem you're working with. Right? So what transfer learning helps is that if you can take off a few of the layers at the end and add your own data, then what you get is that the network will be sort of, in a sense, customized to your problem. Right? You'll have transferred learning that was done previously, extracting features to your problem. So you don't have to learn again sort of the first things in your network. Yeah, and then also the training here differs. You know, you can either start from scratch or use the weights here as initialization. Okay, I think I'm going to stop here. But the idea with this notebook is, please, if you can go through it. So what it really shows, we run some sort of vanilla model. So we take a model, we craft a model here, some sort of model, and we run it, and you get some sort of accuracy. You get some performance. You get maybe 71% accuracy and this kind of thing. And when we do transfer learning, we see that the performance improves, you know, significantly. It goes to the 80s and the 90s, right? In order to do this, we use a lot of data augmentation to create more fake data of the images that we had initially. Yeah. So, and yeah, these are the predictions. So it sort of does relatively well. Yeah. So, yeah.
Is there a way to visualize how it works or how it gets to that outputs, those deep learning models?
Yeah. Mm-hmm.
It's very important to know how it works and how it reaches to that outcome.
Right.
For example, for the problems that have feedbacks, to know whether that person is
Yes, there is a way actually. So that has been an area of study recently. Well, maybe not recently, but people have been very interested in this. So they call them activation maps. How can you, along the pipeline of the network, how can you see what is activating, what is using to make predictions, right? I think the common example is if you're predicting a zebra, is it using the stripes, for example? That would be a key feature to sort of identify a zebra. Or is it using the fact that there's grass in this image, right? So you may have a network that's doing well, but sort of using different things. And so this is important to decipher, and there are ways to do this. There are toolboxes to... Yeah. Okay, I don't have them off the top of my head. There's one that's just been released by. If you watch the Google I/O, there's one that was just released there. I'll check and get back to you. But there are actually tools that do this, unless someone else knows it off head.
Yeah, so Keras has a way you can visualize each layer. So if you look at that code, each layer of the neural network can be extracted, and then you can visualize what is happening to an image at a particular layer. In the documentation, if you just search activation maps in Keras, you'll see how they are trying to do it.
Okay, yes?
I think TensorBoard does something like that.
TensorBoard.
Yeah, you see how it's learning and using it. I think it visualizes learning rates.
Yeah, so TensorBoard is good for looking at the training, but she's, I think, asking about how it's sort of making the decisions it's making based on the land model. Okay, yep. Yeah. So the Transferlining, I think you will see some of it here. So sometimes you have to, you want to answer him?
Yeah.
Oh, okay, go for it.
To what you said about visualizing what happens within the network. If you look at the architecture, you have waves going into a layer, and then you have waves coming out of that layer. Okay? If you imagine the wave going into or out of the layer as a matrix, okay? You can just get a row, you shape it to maybe one side and visualize it and show it out maybe hybrid image show or something, just to see what that layer has learned, okay, for each application. So it's basically matrix multiplication and a nonlinear transformation of that output. Okay, so you can actually get the image from that matrix that you have. So you just pick a row, resize it, and show it. You should see what that's meant. So you can do it manually.
Yeah, so maybe just a quick answer on the Transferlining. Yeah, so it depends. Depends on, so there are many ways, right? So you have TF Hub, for example, TensorFlow Hub. You have the Keras models, which come embedded with Keras. You have those on the Keras website. So these are models that have been pre-built that you can sort of load. But you need to read the documentation. Some of them require that the input image size is of a certain size, and that there's some pre-processing function you call that was applied to the original images. Right? So they require some of them require that, others don't. Right? So it depends on how it was trained. Yes.
Can you say something on challenge in deep learning besides some
Yeah, so I mean, the whole, if you look at the whole NeurIPS, the people working on problems related to this. So there are several types of things people work on. I mean, even just there's AutoML, where you sort of try and predict, what sort of architecture will work for whichever data you have, so you don't even need to handcraft the architecture. It sort of predicts based on what has seen with other data, what sort of network would work best and this kind of thing. There's work being done on model compression. So these models tend to be big because they are deep and the weights are many. So can you compress that to put it on a mobile phone, for example, here where bandwidth is a problem? Those are some areas to work on. Others are sort of in the intricacies of how does it actually work in those the activation functions. How does it work? How do you improve them? How does batch normalization work? Does that help? Does that not help? So for each of the components, I think there's a lot of work going on, but you get the sense of what people have done and what people are doing when you sort of read things like at NeurIPS, sort of see the conference and the proceedings. You get an understanding of what problems people are tackling. But yeah, there are many sort of small nuanced problems. Okay, there's another talk that needs to go on. Okay, so maybe last two questions.
What is the motivation for you to build your own model and you can just do transfer learning?
So I think one, simplicity, as someone said. Maybe you don't want a very complicated model. So maybe you want a simple model. For example, this idea of SNP connections, like in ResNet, people came up with some idea of how the architecture would sort of be aligned to the problem, right? So if you have a problem of the model is too deep, things are sort of getting lost down the line, maybe you need a certain architecture. So there is some motivation to build these different new architectures depending on the problem. So if you can, if you can phrase your problem well, like Benjamin was saying, given this problem, is there any architecture thing that needs to change based on the problem or the way you sort of look at it? Then you can. But normally for a quick start, are things running? You try a simple thing. If it doesn't work, do transfer learning. After that, it's really tweaking, turning knobs. Okay, last, yeah.
As we know, the deep learning is known by its ability to extract features by itself without giving the handcrafted features. But sometimes if we need to give manually crafted features, is there a way to give or supply handcrafted or manually crafted features for deep learning algorithms? In addition to its ability to extract features.
Yeah, so, well, it's trying to solve the problem of you not giving it handcrafted features. But I don't know. I don't know if you can add your own features. I don't know if anyone has some idea. Yeah.
There's the concept of functionality in class. So in addition to the existing layer, we can concatenate the other features wherever we need. We as the middle of the layer or as a primary state, we can concatenate, but the last layer expects the sensitive element. So we have to merge the final array. But there's some portion where we can use some comparison or append to the layer. Using functionality about that is screenshot, I think is good.
Well, I think that's a different, type of problem. There are sort of multimodal layers where you can have maybe images and you combine them with maybe, sequence data or texture data, and you're sort of merging these. I don't know if that's what you meant. Was that what you meant, or you meant, Huh?
On textual data, if I need to add additional features, in addition to the ability to extract features, can I add those features?
Yeah. I don't.
Before you train or after you train?
Before training.
Before the while you train. You can't be while you train. Can you add? Yeah, because you have to fix
size vector.
Yeah, but I mean, you can split that vector into the things that are like handcrafted and then the things you want to learn from, and then you just inject the handcrafted ones somewhere in the network.
Ah, yes.
You can do it later. It would depend on kind of where you expect the handcrafted features are similar to the learned ones. But you want to learn how those things interact. Like Ernest was saying, you might want to have this feature interact with this learned feature so that they create a new one that will help you produce it.
Yeah. Okay. So these slides were put together by Ben. So Ben has done a lot of work. I don't know. Unfortunately, the T-shirts are done. You got a bag. So I will take the bag. Ben will.